Great. Good morning, everybody. It's 9 a.m. Central European Time, so we start this webinar for this morning. I hope you're all in here, and let me share with you. Good day, everyone. Great to see many of you joining in for today's webinar from all over the world. Welcome to our webinar from Planning to Practice, a complete guide to ultrafiltration membrane piloting. My name is Elizabeth Kickert. I'm the Management Assistant at Berghof Membranes, and I will be your host for this session. In this upcoming hour, you will learn practical, proven strategies for successful tubular ultrafiltration pilot studies from our Berghof membrane experts. I'd like to welcome our speakers, Dr. Elena Meabe and Daniel Gonzalez del Pozo. Thank you for being here and explaining your expertise to all of us in this session. Before we start, just a few quick housekeeping notes. This session is being recorded. By participating, you agree to the recording and the processing of your data in accordance with our privacy policy. Second, your camera and sound should already be automatically off and muted. And third, we will start with a short introduction of our company, followed by the presentations of Dr. Elena Meabe and Mr. Daniel Gonzalez del Pozo, and we will finish with a question and answer session at the end. So feel free to submit your questions in the chat throughout. Great. Piloting is not just testing, it is how ultrafiltration projects are won. Performance often cannot be predicted by theory alone. Fouling behavior and operating limits must be tested. Piloting is increasingly the critical decision-making step for validating feasibility and selecting the right configuration. With decades of field experience, we see that well-designed pilot studies consistently accelerate project approval and scale-up success. Our goals are to explain the role of piloting in successful UF projects, bridging the gap between feasibility to full-scale design, share practical insights, lessons learned, and best practices from real industrial pilots, clarify what to test, and how to interpret pilot results to support sound engineering decisions. We help OEMs, integrators, and end users turn pilot data into confident project execution. We think outside the box. We're the leading manufacturer of tubular UF membranes for the filtration and separation of industrial wastewater and process streams, including industries like dairy, food and beverage, landfills, chemical, pharmaceutical, biogas plants, oil and gas, and many others. With more than 50 years of experience and over 2,500 installed systems across the globe, Berghof Membranes prides itself on the robustness, flexibility, energy efficiency, and superior quality of its external filtration membranes and solutions. We're located in 4 sites: Germany, where our manufacturing is held, offices in the Netherlands, Singapore, and Spain. Our core technology is MBR, ANMBR, and direct filtration. We have proven robustness in over 2,500 installations, as explained. Our membranes are available in different tube diameters, materials, and cutoffs, multiple features like standard, backwashable, chemical resistant. We have pilot modules available in different sizes, screening versus scalable. Industrial modules available in different diameters and length up to 71 square meters, unitary service. We have a BCare service and support program, something Daniel will explain more in his presentation. It's involving application analysis, pilot testing, engineering and commissioning, and technical and after-sales support. Now let's get into detail and discover the best practice approaches for designing and executing tubular UF pilot studies. It's my pleasure to introduce our first speaker, Dr. Elena Meabe. Just a short introduction about her. Elena is a manager knowledge center at Berghof Membranes. She's a chemical engineer and holds a master degree in environmental engineering. She's also a doctor in industrial engineering with her PhD research work focused on membrane bioreactor technology and the monitoring of membrane performance. To this day, she possesses 18 years experience in filtration technology, mainly dealing with external tubular membranes. She has a deep insight into the membrane technology for the industrial wastewater treatment market and will now guide us through key insights on today's topic. Elena, thank you for being here. The floor is all yours.
So, hello, good morning.
Yes, you are here. Good morning.
Good morning. Good morning, everyone, and thank you, Elizabeth, for the introduction. And I want to welcome everybody to today's webinar. So today I will be talking about tubular ultrafiltration piloting, why it is important, how to design a pilot study, how to execute it properly, and most importantly, how to translate pilot results into reliable full-scale design decisions. So let's start with a brief reminder of what ultrafiltration is and why it plays such a key role in industrial wastewater treatment. So you know that ultrafiltration membranes remove suspended solids, colloids, oil and grease, macromolecules, bacteria, turbidity, and produce a high-quality effluent. In industrial applications, tubular ultrafiltration is used in many different ways. It can be connected to a biological reactor in MBR and anaerobic MBR processes, where UF separates the biomass from the treated water. Or tubular ultrafiltration can be applied in a direct filtration mode for removing specific pollutants, or for concentrating a specific products, for recovering valuable materials, or it can be even coupled to a chemical precipitation process for RO brine recovery, for metals removal, or for example, softening or cooling tower blow downstreams. On the other hand, it is important to highlight that ultrafiltration performance is often site-specific, and this is the reason why piloting is essential in many cases. So before starting any pilot study, the most important question is, what do we want to learn from it, okay? Typical objectives include assessing treatment performance, such as permit quality for the target pollutants, and the suitability of different membrane cutoffs. Another key objective is defining a sustainable design flux under certain operational conditions. Moreover, pilot studies also allow us to optimize operating conditions, such as cross-flow velocity, fouling control strategies, CIP protocols, always trying to balance the performance with OPEX. And finally, piloting is a powerful risk management tool. So it provides real data for scale-up, validates pretreatment requirements, and helps identifying operational risks in an early stage. So well, once we define the objectives, the pilot must be designed accordingly in terms of scale, pilot assembly, and monitoring strategy. So, well, pilot studies can be performed at different scales, and each scale serves a different purpose, okay? So we have the screening modules, which are typically used to evaluate whether a membrane is suitable for a given wastewater, or for comparing the performance with different cutoffs, and also observe fouling behavior in a first step. Then we have the scalable pilot modules, which on the other hand are designed to better reflect real operation conditions, okay? They allow accurate measurement of pressure drops, permeability, and sustainable flux values that can be directly transferred to the full-scale design. So when designing a pilot plant, several practical aspects must be considered. First, the operation mode. Are we thinking on short-term batch testing, or do we need long-term continuous operation? Second, the configuration of the UF pilot. It can be based on feed and bleed configuration, or it can be a simple circuit with just a recirculation pump and some instrumentation. We also need to design about fouling control and evaluate the need for including, for example, backwash sequences. Okay, if we want to approach the project with a V-Smart Eco mode, which relies on backwash sequences for reducing the cross-flow velocity and therefore reducing or minimizing the energy consumption. Third, we need to decide about monitoring and control. Manual operation can work for short tests, but automated operation with data logging and remote monitoring is strongly recommended for larger scale demo units. And finally, we need to define the upstream process. In biological applications like MBR or anaerobic MBR, we can find two potential scenarios. Okay, the UF pilot can be connected to an existing bioreactor or to a dedicated tank built for the pilot study. One or the other have different implications that we will cover later in the webinar. And then in direct filtration applications, we need to install proper feed and concentration tank, and we also need to decide how to handle the reject and the operation mode. For example, batch or continuous reject. Okay, in this slide, you can find a summary of the main parameters typically used to evaluate ultrafiltration performance properly. Pressures, including pressure drop and TMP, transmembrane pressure, tell us how the membrane is being loaded and how fouling develops over time. Cross-flow velocity is one of the most important parameters in tubular ultrafiltration, as it directly influences shear stress, fouling control, and energy demand. In feed and bleed systems, the concentration factor inside the filtration loop needs also to be selected and controlled. And in concentration processes, global recovery and its impact on permit flux must also be evaluated. Then flux and permeability are the core performance indicators, and also normalizing them with temperature allows meaningful comparison over time and between different operating conditions. Okay. And it is also important to note the relationship between these parameters represented in the figure that you can see in the slide. Okay, this is the typical performance of cross-flow filtration systems. You can see how flux behaves based on transmembrane pressure and how cross-flow velocity impacts the flux. Okay, so usually there is a first region, pressure control region, when there is a linear increase of flux with TMP and where cross-flow velocity has minor impact. Then there is a transitional region, and finally we find the mass transfer control region, okay, where flux remains constantly independently of the increasing TMP. This is the so-called limit flux and is commonly increased when operating at higher cross-flow velocity. Okay, as described in this slide, a successful pilot follows a stepwise experimental plan. We start by clearly defining the objectives and selecting the membranes and configurations to be tested. Then we establish baseline operating conditions using normally conservative values to ensure stable operation and reproducibility. Next, we define the operating ranges for key parameters such as flash, close flow velocity, TMP, recovery, usually covering both normal and stressed conditions. Then the pilot study itself is divided into phases. We have the startup, optimization, long-term operation, and also stress testing if desired. And finally, also, we need to define a monitoring plan and clear success criteria so that the results can be directly translated into design and decision making. Okay, now my presentation, I will be mainly focused on the lab and bench scale pilots, okay? These are typically short-term studies, and their main objectives are to assess permit quality, identify an initial sustainable flux range, and evaluate the influence of key operational parameters. These pilots are particularly useful as a first step to screen membrane options and define a realistic operating window before moving to a larger scale piloting. So, here you can see the basic elements required for the most simple bench scale pilot. So you have the feed tank, you have a recirculation pump, you have the pilot module. Then in the retentate stream or the concentrate stream, we need to install a regulation valve. It can be a manual regulation valve that we use for pressurizing the system and also for controlling the transmembrane pressure. In terms of instrumentation, it is quite basic. We need pressure indicators or transmitter at the inlet and outlet of the module, and also something to measure the recirculation flow so that we set the cross flow velocity for the experiment, and something for measuring the permit flow. Okay, it can be even measured manually with a graduated cylinder and one stopwatch. And usually both permit and retentate are connected to the feed tank. This enables us to operate in recirculation mode and also to allow the feed tank to be used as a CIP, as the cleaning tank. Here you can see a picture of our bench scale VSCAN pilot. The procedure for a lab scale pilot usually starts with a clean water flux test to establish the membrane reference condition. Then we evaluate the filtration performance under fixed operational conditions. For example, cross flow velocity of 4 meters per second and TMP of 1 bar. Usually this first stage is done in recirculation mode. Okay, so we put the permit stream back into the feed tank to assess a first general value for the flux. Okay. Afterwards, the system is operated in concentration mode, discharging the permit from the system to achieve achievable recovery and system stability. And finally, we investigate the influence of operational conditions, mainly cross flow velocity and transmembrane pressure. And after the filtration test, we can perform a CIP cleaning to evaluate the cleaning efficiency and also the fouling reversibility. This slide shows an example of a bench scale pilot, in this case treating laundry wastewater. Okay, so on these graphs, in the first one, you can see how permeability and recovery evolve over the test, over the time. So you see a first stage here operating in recirculation mode, zero recovery. After some time, when we see more or less a stable permit flux, we start working in concentration mode, okay, discharging the permit from the system. You see here the evolution of the recovery. So here, what we can evaluate is the impact of concentration on the permit flux. This impact can vary a lot depending on the wastewater sample that we are dealing with. Here, for example, we see an initial decrease of permeability, but approximately at 45% recovery, the flux remains constant. So once the target recovery is reached, it was 90% in this case, we leave the system operating in recirculation mode, again, basically for assessing the flux stability at the target recovery. Therefore, we evaluate the influence of operational conditions. The result is shown in this second graph. For this, we fix the cross-flow velocity at the maximum value that we want to test, let's say 4 meters per second, and gradually increase the transmembrane pressure in steps, okay? Each step lasts for 10-15 minutes. So for each TMP value, we will obtain a flux value. So we test at 4 meters per second, this is the blue line, and once we have the curve, we decrease the cross-flow velocity, let's say 3 meters per second, and repeat the procedure. In this case, what you see is that at cross-flow velocity of 2 meters per second, fluxes are significantly lower, and moreover, the limit flux is reached at quite a moderate TMP. And in parallel, what we see is that the results at 3 and 4 meters per second are basically the same, okay? So by doing this kind of a test, we can decide the best cross-flow velocity for achieving the lowest energy consumption in each specific project. In this case, it could be 3 meters per second. And finally, we can apply a chemical cleaning to assess the most efficient protocol. So, well, as I am approaching the end of my presentation, I just want to share some comparisons of pilot results with different wastewaters and a couple of practical tips. Okay, so, well, here in this case, you can see how these flux TMP cross-flow velocity curves are a very powerful tool in UF piloting. Okay, and well, they show how flux responds to TMP and cross-flow velocity, and clearly illustrate the trade-off between performance and energy demand. So here, by comparing results for different wastewaters, we have MBR sludge, we have direct filtration of digestate, lime softening for aerobrine recovery, and also UF coupled to chemical precipitation for copper removal in this case. And you see that the results differ significantly between different type of wastewaters. And this is why it is super interesting to have this kind of results in the lab scale pilot test. If we look, for example, at the digestate case, as you might know, digestate is a very challenging stream with high TSS and with low filterability, okay? And in these conditions, the impact of cross-flow velocity is very important. With low values, we see almost a flat line. Limit flux is achieved at very low TMP values. So therefore, for these cases, we will select the maximum cross-flow velocity, which in this case is 4 meters per second. However, if we look, for example, at the fourth graph, ultrafiltration coupled to chemical precipitation for removing copper in metal industry wastewater, we see first a linear relationship between flux and TMP. This is very good. This means almost negligible fouling together with high permeabilities. But apart from this, what we see is that there is no impact of cross-flow velocity, okay? These are, let's say, inorganic particles that are not really getting attached to the membrane surface. So in this case, and based on this result, we can approach the design with low cross-flow velocity of 2 meters per second and minimized energy consumption, okay? Okay, this is my last slide. I want to share also examples of optimization of chemical cleaning protocols, okay? Again, with quite different outcomes for different wastewaters. So, well, first, in this case, it is MBR for digestate treatment, okay? We see that the initial alkaline cleaning recovers permeability to a great extent, which is logical because in MBRs, fouling is mainly organic, okay? But we still see an important improvement with the acid cleaning. In this case, this is due to the high hardness present in the digestate, which produces some kind of inorganic scaling. We have this second example. It is oily wastewater, direct filtration for removing emulsified oil from water. Here, what we were testing is a standard alkaline cleaning with sodium hydroxide and sodium hypochlorite with alkaline cleaning, but adding a degreasing booster, okay, during this alkaline cleaning. You can see the difference is really important. Here below, we have another example. This was cosmetics wastewater, okay, direct filtration. Again, we see that applying an enzymatic cleaning with a commercial enzymatic membrane cleaning product is improving significantly the efficiency. And then we have this final example where we compared standard chemicals, let's say sodium hypochlorite plus sodium hydroxide versus commercial alkaline cleaners. We were testing cleaners from two different suppliers, okay? And you see, again, that the result is important. The difference in result is important. These membranes were deeply fouled. It was organic fouling, but we see that the results clearly show that alkaline commercial cleaners are not only more effective, but also significantly faster at removing the organic fouling. So that this is the last information that I wanted to share today. I hope that I have been able to transmit the importance and usefulness of proper piloting. And well, I will be happy to answer your questions at the end of the webinar. So with this, I end up my presentations. Thanks you very much for your attention, and well, we will cover any question at the end. Thank you very much for your attention.
Great. Just waiting for my screen to load again. Thank you, Elena, for sharing your knowledge in this presentation. Before we continue, just a small reminder, as Elena said, that we will discuss questions after the following presentation of Daniel. You can submit your questions in the Q&A. Great. Now it's my pleasure to introduce our second speaker, Daniel Gonzalez del Pozo. Daniel is Service and After-Sales Manager at Berghof Membranes. He is a professional in water treatment with over 2 decades of experience. He holds a degree in chemistry and an advanced master's degree in water treatment and environmental safety, complemented by an executive MBA. Before he joined the Berghof Membranes team, he fulfilled leadership roles at Quantum Water Engineering and GE Water. Daniel brings a strategic vision to solving complex global water challenges and will be sharing with you his practical perspective following the pilot phase. Thank you, Daniel, for being here today. If you are ready, then the floor is all yours.
Hi, Elizabeth. Thank you very much. Let me share the screen. Just a moment. Set it in presentation mode. Here it is. Okay, good morning, everyone, and thank you again for joining us today. I want to talk with you about something critical to the success of any filtration project, which is the pilot phase. Okay, so whether you are developing a new treatment process, scaling up an existing one, or validating your approach before making a full-scale investment, piloting is key to success. So at Berghof, we try to make this journey as smooth, efficient, and reliable as possible. We understand that moving from concept to full-scale operations is complex, so there are technical uncertainties, operational challenges, and of course, financial risks. So that's exactly why we have developed piloting capabilities and services designed to de-risk your projects, optimize your systems, and give you the confidence to scale with a high grade of certainty. Okay, so let me start by giving you an overview of what we offer. In that sense, we don't only provide equipment, but we provide a complete end-to-end support. So we can start with, for instance, our pilot modules. We help select the optimal module size for your goals. We offer a wide range of pilot modules that should match your specific needs. Additionally, we also provide what we call engineering packages. We deliver engineering support, so it basically means the complete engineering package for your pilot unit design. On the other hand, we have the possibility of conducting lab tests, as Elena showed you before, and we can evaluate your wastewater using benchtop ultrafiltration systems at our lab to see how our membranes perform with your specific fit. And a bigger scale, we have our pilot plants for rental. They are containerized pilot plants. They are fully equipped, are mobile systems which are deployed for testing under your current conditions on site. So besides all of this, to support our customers during this journey, we also offer commissioning support. So we provide on-site commissioning support with our service personnel to ensure a successful startup. And during the pilot tests, we support our customers by remote monitoring. So we can track your pilot and ensure its performance over the length of the trial. Okay, so let's go deeper on that. Firstly, let's talk about our pilot modules. We offer flexible module options for different ranges. So firstly, our P1 module can be supplied in a wide range of options. For instance, either in PVDF or PES active layer, different cutoffs, and tube diameters from 5.5 to 12.7 millimeters. The P1 Flex module gives you exchangeable membranes for testing, so it's a very flexible option. Besides, we have the P5, 13, and 22 modules, which offer increasing capacity. Contrary to the P1 modules, which are fitted with a single membrane tube, these pilot modules have some tubes, so they can produce higher permeate volumes. Just let me remark that generally all of them are intended or lab scale tests. But, however, we have our 315G module, is our largest option for higher throughput applications. This module, which is also provided with a wide range of options, it is intended for semi-industrial scale piloting. So the key here is flexibility. You can choose the configuration that fits your specific needs. Okay, let's focus now on our containerized pilot plants. They are fully operational, actually, with everything you really need. They are suitable for different type of applications, such as, for example, MBRs, anaerobic MBRs, direct ultrafiltration, ultrafiltration coupled to chemical precipitation, so on and so forth. Our pilot units can be operated in what we call eco mode, for reduced energy consumption with automated backwash, or performance standard mode to maximize output or permit production. The systems can operate at permit flow rate control, okay? Or you can work on the premise of controlling TMP, or transmembrane pressure. You can run up to 4 modules in series, as you can see in the picture, giving you high flexibility. What else? Yeah, operating data is automatically logged, and the system can be operated and monitored remotely, okay? So in the end, we also see what's happening at your site in real time, and we can take control if it's really needed. Okay, what do you need for a containerized pilot test? Okay, you will need basically tap water for flushing and CIPs, compressed air for the pneumatic valves, and a three-phase electrical supply, okay? Internet connection on site, if available, is very useful, although the pilot units are also fitted with a router and SIM card. Well, depending on the application and facilities available on site, you might need a feed tank or bioreactor for aerobic and anaerobic treatments, okay? Finally, a very important matter to take into consideration, I will talk about this later as well, is pre-treatment. A proper pre-screening is necessary to avoid any issues during the pilot tests, such as clogging events, for instance. Okay, so how is all this put into motion? Okay, well, we start with technical proposal and quote. Okay, that's quite normal, obviously. And afterwards, we usually hold a preliminary meeting to evaluate your site requirements, okay? So once we receive the purchase order, we start organizing the shipment of the pilot units to your site. To assess that everything has been arranged properly, we provide what we call a pre-commissioning checklist, which must be signed and sent back to us, okay? Then, once everything is ready, our team arrives for 1 week on site for commissioning and training of your staff. So throughout the pilot tests, we provide remote monitoring and technical support as well. And after finishing the trial period, we deliver a final report and eventually technical proposal for the full-scale project. What are we actually trying to achieve in these pilot tests? Well, a proper pilot should determine achievable permit quality. We must evaluate flux stability over time. Okay, we need to optimize operating conditions such as TMPs, flows, backwards frequency and duration, and so on. Different cleaning strategies and the chemical consumption as well. And we must, of course, evaluate energy consumption and operational costs, okay? So in the end, all these matters are essential for a full-scale design. Okay, now let's have a look at our experimental approach, okay? So we follow more or less a structure plan here. So firstly, we define a baseline of operating conditions conservatively, okay? So secondly, we stabilize the system and verify a steady operation. Once this is achieved, we start increasing flux stepwise to find basically maximum stable flux, okay? We also evaluate the impact of cross-flow velocity on performance and energy use. And additionally, we assess backwash frequency and duration, if any, of course, because not in all applications backwash is applicable, and as well chemical options, chemical enhanced backwash, for instance, you know. Another important matter is to optimize the cleaning in place approaches. And finally, we define sustainable operating conditions that they are suitable for a scale up. So in summary, this is a systematic approach that gives you reliable data, and it's not based on either assumptions or preconceptions. Well, this is just an example of test for an MBR, okay? Please have a look at the graph on the slide here, okay? There you can see how we were increasing the permit flushes over time. This is the orange line, okay? We started with approximately 50 or 45, I would say, flux LMH. And then we have been increasing the fluxes. The blue line is the transmembrane pressure, okay? So you see how the membranes react to the increase of flux. And we reached that point where the fluxes were unstable or unsustainable, okay, here, okay, for instance, at around 90 LMH in this particular case. And you have seen this sharp increase in the TMPs, okay? So, later on, we reduced the fluxes again, and we have seen a recovery in the TMPs. So it is good news, obviously, because it's reversible fouling, okay? So later on, we try again to see if those high fluxes were sustainable, but we have seen a high increase in the TMPs again, you know, so, okay. So this is how we determine sustainable operating conditions, monitoring the behavior of membranes under different conditions. Okay, well, I'd like to finish this presentation with some practical tips. So let's talk about some practical insights here, okay? For example, the integration of pilot units to existing bioreactors, okay? So for biological treatment, connecting to an existing full-scale bioreactor can be somehow problematic because you inherit its conditions. So consequently, we often recommend a dedicated pilot scale bioreactor for true optimization. So, well, among other reasons, there are a couple of them I would like to point out here. So the first one is pre-screening. The presence of core solids or fibers, hairs, that they don't have, I would say, a significant impact in conventional systems can cause serious issues in MBRs, in anaerobic MBRs. So a proper pre-screening upstream the pilot scale bioreactor will minimize these potential risks. And on the other hand, one of the main advantages, as you may know, of both MBRs and anaerobic MBRs is the possibility of running the system at much higher MLS concentrations. So to simulate this in pilot test, a pilot scale bioreactor is needed, obviously, in order to get those working conditions. Well, let's move to something a little bit different. This basically how to operate the pilot unit. Well, as you may see on this slide, there are several options. For instance, we can operate in continuous mode, okay, which is, well, quite common for MBRs and anaerobic MBRs pilot test. We also can operate in semi-continuous mode, okay, and of course as well in batches and semi-batches. These last two are quite typical for data filtration applications where you are looking for a highest level of concentration of the fluid to be treated. Well, going back to this previous topic I mentioned, which is pre-treatment and pre-screening of the wastewater. Well, actually, it is quite critical, okay? So the standard practice is 0.75, 0.8 millimeter mass, or 250, in the range of 250, 350 microns. If you foresee the presence of fibers and hairs in the wastewater. So, sorry. In this sense, a simple sieve test will tell you exactly what pretreatment you really need. And on this slide, well, you can see several pictures of different wastewaters and the kind of material retained by the pre-screening, okay? So depending on the case, this pretreatment approach must be evaluated, okay, to avoid any issue during the pilot tests. Well, yeah, let's talk about something different. Another usual topic of discussions, to be honest, is the biomass control in MBRs, for instance, you know. Yeah, please do forget about V30 and SVI, which are common follow-up parameters for conventional activated slats. But in reality, these stability measurements don't matter in MBRs because the membrane is actually a physical barrier, okay? So not having, I would say, a significant effect on the performance of the membranes. So instead, we should focus, for instance, I would say on permit quality, flux stability, TMP trends. Okay, this is basically exactly what really matters in MBRs. Okay. Yeah, finally, this is my last slide for this presentation. The permit quality, okay? Yes, a couple of remarks. Well, our membranes always produce suspended solids-free water because they are in the range of ultrafiltration. However, there are a couple of things that I would like to remark here because sometimes they lead to wrong conclusions, okay? So the first one is the fact that ultrafiltration removes apparent color, but not true color. So if dissolved organic matter or some ions are producing color, you need additional treatment to remove it, if it's really needed, obviously. For instance, filtration by activated carbon, nanofiltration, or reverse osmosis. On the other hand, as well, be careful with lab analysis on high salt wastewater. Dissolved salts can create false suspended solids readings or data, okay? For these particular cases, as it is stated in the general protocol to test it, the filters must be washed several times before drying them out, okay? To obtain a real value, okay? Well, then to wrap up, just I could say the main takeaway of all of this is that piloting plays an important role in the design of a full-scale system, especially when there are a high level of uncertainties in the correct approach for a new project. Okay, so in this regard, will help you de-risk your full-scale investment and optimize operating conditions from the very beginning. Well, that's the end of my presentation, and thank you very much for your time. Elizabeth, it's back to you.
Thank you, Daniel. I'll just start sharing again from my end here. And wait until it's loaded. I think we're all here now again.
Yes.
Yeah, great. Thank you, Daniel, for your presentation. I'm sure this was very insightful for everyone attending today. Now it's time for questions. So we will move into the questions and answers session. So we have roughly 7 to 8 minutes left into this webinar. So feel free to submit questions if you have in the Q&A. And let's start with the first one. Daniel and Elena, I think you're both here again. Great.
Yes.
First one for Daniel. How many pilot plans do you have available for rental? For which membrane types and flows?
Okay, apart from a couple of small units that we have for lab tests, okay, these are basically, well, in terms of, I would say, permit flow that you can attain per hour, maybe 10 liters per hour, something like that. They are basically in that range. Then we have two containerized systems, okay? So these containerized systems, depending on the applications, but in terms of permit flow, we could talk about between 200 to 1 cubic meter, 200 liters, sorry, to 1 cubic meter per hour, roughly, okay? Something like that, okay? Permit production, I'm talking about permit production, okay? And in that sense, apart from the capacity for membrane options, we have all the with our pilot units, we have all the portfolio available. Okay, from active layer made of PVDF or PES, different cutoffs. You know, for instance, 30 nanometers, 100 kilodaltons, 50 kilodaltons, well, all of them. What else? And then the diameter of the membrane tubes, okay? Depending on the applications, we have the capacity of choosing the right one. We have a portfolio, as I said in my presentation, from 5 millimeter diameter to 12.7 millimeters. So yeah, we have a wide range of options here. Yes.
Right. Okay. I hope that answers the question. I have a next question for Elena. Have you encountered calcium fluoride contamination during CIP cleaning? Sorry if I mispronounce anything of this. Do you have any recommended steps for cleaning calcium fluoride scale?
Okay. We have a certain previous experience with fluoride precipitation as calcium fluoride. Okay. This experience is from the application point of view. I don't think we were facing like significant scaling problems with calcium fluoride, but this is because in our case, when we approach this kind of, I think it was in microelectronics industry, when we approach this application of removing fluoride, it is by means of what we call ultrafiltration coupled to chemical precipitation. So we have this previous step where we precipitate fluoride as calcium fluoride with high pH. And then what UF is facing is basically a mix of clean water plus inorganic solids. If everything is done properly and controlled, calcium fluoride should not cause any scaling in the UF membranes because it is already in the form of particles. For doing this properly, it is very important to control the pH and also the hydraulic retention time, the contact time during the precipitation phase. Having said this, it is true that calcium fluoride, I think it is quite a difficult inorganic product, very low solubility. The cleaning options are always with strong mineral acids, I think. Probably at pH of 2 or even lower should be beneficial. So if this is the case, we could be approaching the project with our CR modules with higher chemical resistance so that acid cleaning can be applied even at a low pH of 1. Okay, so this is our experience.
Right. Okay. We have time for another question. So this one is also for Elena. What is the maximum total solids concentration for the liquid digestate to be able to pass through the UF system?
Okay, there we have like 2 options. Let's say we think on the 8 millimeter membranes. We have quite a lot of experience with them for direct filtration of digestate. How we approach the projects normally is having maximum 30-35 grams per liter of suspended solids in the reject. Okay, so based on the inlet concentration, we will decide the recovery that we apply for the ultrafiltration. More recently, we have also developed these bigger diameter membranes with 12.5 inch diameter in the end. And with them, we have experience where we have reached up to 60-70 grams per liter in the reject.
Great. Okay. 1 more minute. So last question, I suppose. Which are the membrane materials and pore sizes available? This is a question for Elena.
Well, in terms of materials, we have both PES, polyether and PVDF. And in terms of pore sizes, we cover like a big ultrafiltration range between what we call fine ultrafiltration, this is 5 kilodaltons, and up to 30 nanometers. 30 nanometers, for you to have a reference, is the membrane that we commonly use for applications such as MBR, anaerobic MBR, this type of applications. I would also like to notice that I saw, as I was referring to anaerobic MBR, I saw some question regarding the COD removal that we can achieve in an anaerobic MBR process. I would say that according to our experiences, we have quite a lot of references in dairy wastewater, for example, and we can achieve even more than 98% COD removal. We have also references in distilleries where we can achieve more than 95% removal. Thank you.
Okay, thank you, Elena. Yeah, concerning the time, I think we have to leave it here. So I'm afraid we have to answer any other questions you might have another time. So yeah, if you have questions that we were not able to discuss, or if you need more information, whether it's technical information or you want to evaluate your pilot projects and plans, or perhaps you're interested in renting a pilot unit for an on-site demonstration, please get in touch with us. The details are listed right here. Subscribe also to our newsletter and follow our LinkedIn page if you haven't done so, so you can stay tuned for our latest news and upcoming events. Lastly, I'd like to thank both our speakers, Elena and Daniel. Thank you for sharing your expertise today. Thank you all for attending to you all and participating. We hope you find this session valuable, and we look forward to connecting with you here in the near future. So everyone have a lovely day, and see you all next time. We end this webinar now. Thank you.
Thank you, Elizabeth.
Thank you.
Bye-bye.